several variables, right? So that sounds fancy, lots of words there. But what we've been doing all year is calculus of functions of a single variable, something like f of x. And in this chapter, we'll be taking all those techniques and sort of bumping them up a level to, instead of just a function of one variable, where you have one input, we'll talk about functions of more than one variable. Okay, so 7.1, the start of chapter 7. We're just going to introduce functions of several variables, right? So functions of several variables is just, instead of a function of a single variable, there's more than one. Right? So instead of x, we have x and y be variables, something like that. So that's the main idea, but let's go through that. So what is a function of several variables? Well, let's start with reminding ourselves what is a function. Right, so remember a function, this is a throwback to the very first lecture that we had in chapter 1, is a function is a rule that assigns to each input exactly one output. Right, so something like f of x is 2x or 3x squared, something like that. That is a function. It's a rule every input has exactly one output. And when we dealt with functions, we talked about functions whose input was just one thing, something like f of x, and x, that single thing, was the input. So that's a function of one variable, but what would a function of more than one variable look like? Well, it's just going to be more than one input, right? So it's still a rule that assigns to every input exactly one output, but instead of inputting just one thing, we're going to input more than one thing. Right, so to define that explicitly, a function of two variables assigns each input pair, right? Here we have a pair x comma y. That's the input. Both of those, they have to come together. And it's going to assign a number and exactly one of them, and we call that f of x, y. Right, so that would be the function f. It's a function of two variables. Inputs a pair x and y, outputs a number in terms of whatever those x and y's were. Function of three variables would do something similar. This time you'd have to input not just x and y, but a triple function of three variables. You need three pieces of information for that input, and here that would be something like x, y, z. And that's still going to output exactly one number. What depends on x, y, and z, right? Whatever you input, it's still, the output is just a single number, but the input here would be a triple. X functions of 4 variables or 7 variables, and you could just input a bunch of different things, but we'll stop at just the 2 and 3. Let's talk about what do these things look like, right? So if you were to look at a function of 2 variables and graph it, what does that look like? Well, it doesn't, you can't draw it on like the XY plane on the whiteboard like normal, because it has 2 pieces of information for the input and then outputs a number, as opposed to 1 piece of information and then outputting a number. So that means you need 3 spaces to put things when you're talking about the output. You need the x and the y and the output number. So instead of something like this on the left, that would be something like f of x, a single variable. Instead of it being a line drawn on a plane, we have a surface drawn in 3-dimensional space. Ooh, fancy, fun, right? So here we have f of xy, right? Notice the input is 2 variables. So this would be a function of 2 variables, x and y. So let's say whatever that might be, let's say you input 2 comma 3, then it would spit out 3. So what that tells you is that something like f of 2, 3 equals 3. And that gives you that point 2 comma 3, that came from the input, and then the output was that last 3. And that is a point in what's called three-dimensional space, where you have three variables, x over here, y over here, and z over here. All right, and so those outputs just look like surfaces. But notice this point here is still special. Right? There's something to be said about the way that this surface looks, and maybe there's a special point there. But we'll get to that. Oh, and of course you can't see my note now. So what did that say? Well, that just says that points on the graph look like xy, f of xy, which is what I pointed out here with 2, 3, and then 3. Right, so the points here have 3 locations, one x, one y, and one z. Things that tell you where that point is. Okay. Here's another example of a graph of a function of 2 variables. All right, so again, it's a surface. You could think of it as like it's a piece of paper floating around in three-dimensional space. But depending on what that function is, that can be twisted and moved around, and so it's not flat like a piece of paper, but maybe it's curved, and we call these things surfaces in three-dimensional space. But those are more examples of what the graphs might look like. Okay, so now let's just do some examples with these functions of 2 variables. So I'm going to give you a function of 2 variables and just say find a couple of output values. So what would f of 0, 0 be? Well, f of 0, 0, whoops, that means you want to plug in x equals 0, that's this guy, and y equals 0, that was the other 0. Right, so this is x comma y. So now let's go to our function. It's e to the x, but here x is 0, so that's e to the 0, times, it's y cubed, but y is 0, so that's 0 cubed, plus 3 times y, but again, y is 0, so we're just plugging in x equals 0 and y equals 0. Whoops. Wrote down y. That should be y equals 0. So we want 3 times 0. And what do we get? That's 1 times 0 plus 0. That's 0. So f of 0, 0 is 0. And if I asked for that point on the graph, you would have to give me the first 2 guys, x and y, and then the output would be that guy. Okay, what about f of 1, 2? So for f of 1, 2, the first guy is the x. So x equals 1, and the second guy is the y, so y equals y equals 2. There we go. Okay, so we're plugging in x equals 1 and y equals 2. So e to the x is e to the 1 times y cubed is 2 cubed plus 3y is 3 times 2. So what is that? Well, that's e times 2 cubed is 8, so that's 8e plus 3 times 2 is 6. Right, so there is the output, and if I wanted that as a point, I'd have to do x comma y comma whatever that output. Okay, now let's do a function of 3 variables. All right, so I have f of x, y, z, and then it's a bunch of stuff with x's and y's and z's. And I want to find f of 0, 0, 0. So this first 0 here, that's this x, so that means we're plugging in x equals 0. The second 0 is this y, so that means we're plugging in y equals 0. And the third 0 is what z is, and so z is also 0. So let's plug in 0 for x, y, and z. We get 3 to the 0 for y minus 7 times 0 for x times 0 for z plus 0 for the y squared, and that's 3 to the 0 minus 0 plus 0 is just 1. So there's our output there. All right, now let's find f of 1, 2, negative 1. So again, the first thing says that x equals 1. You don't have to write this part out. You do not have to write that out. That's just whenever you're doing these on the homework and stuff. But the first guy says x equals 1, the second guy says y equals 2, and the third guy, that's what z is, so we're plugging in z equals negative 1. So what is 3 to the y? Well, that's going to be y equals 2, so 3 squared minus 7 times x is 1 times z is negative 1 plus y, which is 2 squared. So what is that? Well, 3 squared is 9 minus 7 times 1 times negative 1 is negative 7, so that's going to become plus 7 plus 2 squared is 4. So what is that? Oh, that's 20. So that's the output for 1, 2, negative 1. The output is 20. All right, how about I'm going to give you a function of 2 variables, but what I want you to do is find something like this. So you should see that and immediately think, that looks vaguely familiar. I remember dividing by an h and doing something like an x plus h somewhere, yada, yada, yada. Hopefully that's familiar. And in fact, that looks a lot like a difference quotient, and that's because it is a difference quotient, right? We are taking the difference between an x plus h and an x for what we plug in, dividing by h. Notice this y is left alone. Right, so y is going to be the same, but in the first guy we're going to plug in x plus h. In the second guy we're just going to plug in the x. We want to find and simplify that difference quotient. Right, so this should make you think, well, maybe we're going to start taking the limits of this thing. And in fact we will. But let's first just do this. So this is the difference quotient where x is changing. Notice y is staying the same. X is the only thing that's changing here. So let's figure out what is f of x plus h comma y. This part right here. All right, so let's just do that. And I'm going to do this in pieces here, just for the first time we do this, to make it hopefully more clear, and then we can put it all together whenever we do this from now on. But let's first just find what I boxed in red there, f of x plus h comma y. So we're plugging in x plus h instead of this x, so in the x slot we're plugging in x plus h. So that's 2 times, and it's an x here, and that means whatever's over here goes right there, so x plus h. And notice I put parentheses around that because it's 2 times that whole thing, not just 2 times x plus h, right? So that's the difference between 2x plus h. That's not the same thing as 2 times x plus h. And this is the way we want it over here, where we plugged in the whole x plus h where the other x was. All right, but that should be familiar, hopefully, because we did that back when we just did difference quotients of a function of one variable. Okay, so we plugged in x. Now we want to plug in y, but y is just y. It didn't change. So y squared, there it is. And that's f of x plus h comma y. This f of xy, which we're going to subtract, is just this guy, so I won't write it down again, but that's going to be that thing. And then we have the h on the bottom. So let's put that all together. Switch back to red here. All right, so the difference quotient, I don't want to rewrite that, but this thing, rewrite that is equal to, now let's copy down what we got for f of x plus h comma y. So that was 2 times x plus h minus y squared. So that's f of x plus h comma y. And we want to subtract the original just f of xy, which was 2x minus y squared over h. So there's the difference quotient. We do want to simplify this thing. Now remember, when we simplified difference quotients for functions of one variable, a bunch of nice things happened. And what we got was that as long as we did everything correctly, right, if we didn't make any mistakes, then everything in the numerator that did not have an h canceled, and we were able to factor out an h and cancel it with the h on the bottom. That should still happen. So let's double check that it does. So to simplify things, let's first distribute this 2 through, and we get 2x plus 2h minus y squared. And then we'll distribute this negative guy through, and we'll get minus 2x plus y squared over h. And now notice we've got a positive 2x and a negative 2x, so those cancel. We've also got a negative y squared and a positive y squared, so those cancel. And the only thing that's left is something with an h in it, so that's good. We have 2h over h. And now we can see that we can cancel that h, and we're left with just 2. So there is the simplified difference quotient. Right, so I want you guys to take a minute, look at that, hopefully recognize the similarities between this and finding the difference quotient of a function of one variable. And then I want you to take a second before you move on in the video and see if you can figure out where this 2 came from. So you guys hopefully remember that when we started taking difference quotients, that led to us taking derivatives. Right, so by another example, what I mean is this is the exact same function, but now we want the limit as h goes to 0. So let's take the limit as h goes to 0, but we already found that difference quotient, and it was 2. So what's the limit as h goes to 0 of 2? That's just 2. All right, so that one was easy. This limit as h goes to 0 gives us a derivative of some kind. It's not a complete, not a full derivative of this function, but it's the derivative that has to do with just x changing. Right? We'll talk about that. That's going to be 7.2, but that gives us a derivative where the only thing that was changing was x. And in fact, we'll go ahead and introduce that verbiage here. What we say is that that is the partial derivative, right? So it wasn't the complete derivative because only the x changed. So we call it the partial derivative with respect to x, right? And that's because it wasn't everything x and y changing, but just whenever the x is changing. And we take this limit, right? This should look a lot like the limit, should remind you guys, because it does look a lot like the limit definition of the derivative that we've seen before, where here only the x is changing. But we'll talk more about that going forward. So let's look at this exact same example here of f of xy. And I do want to find and simplify a difference quotient again, but this time notice that the thing that's changing is the y, and the x is left alone. All right, so this would be the difference quotient where the y is what is changing. All right, so let's see if we can do this. What is f of x comma y plus h? So we're going to go over here to our f of xy. Here, we'll do this one off to the side. And I'll even do it in a different color. So just this thing. What is f of x comma y plus h? Well, that means we want to plug in just x equals x. And instead of y, we'll plug in a y plus h, right? So 2, and then the x is still an x, minus, and then wherever that y was, which was right here, we're going to plug in whatever's in this second slot, which is y plus h. And again, parentheses are important there. And it's y plus h, that whole thing squared. Okay, we know we're going to need to simplify some things, so let's go ahead and expand that squared guy out and see what we get. So we get 2x still, and then minus y plus h squared is y squared plus 2 times yh plus h squared. And if you don't believe me, go ahead and double check it. Now I want to distribute this negative sign through because I know I'm going to want to do that. So that negative becomes a negative y squared, and then instead of pluses, we'll be left with minuses. So this will be minus when we distribute that negative sign through. Okay, so f of x comma y plus h is 2x minus y squared minus 2y minus h squared. And that's because we expanded this guy out and then distributed the negative. So now let's take that and plug it into the difference quotient here. So this whole thing is equal to, we're going to plug in what we just got, 2x minus y squared minus 2yh minus h squared, and then subtract the original f of x comma y, so that's what we started with. All right, now just like back in chapter 1 or 2, I think it's 2 and 1 actually, when we talked about this stuff, and just like the last example where it was the x changing, when this y is the only thing changing, you should still have that all the stuff in the numerator that does not have an h should cancel. Then you should be able to factor out an h and cancel it with the h in the denominator. Right? So that should be something you're familiar with after doing it just now, and hopefully remembering us doing it before. So what does that look like? Well, if we distribute this negative sign through, what do we get? Well, we get that we have a minus 2x, but then it's going to be plus y squared. And now I've got a positive 2x and a minus 2x, so those cancel. And I've got a minus y squared and a positive y squared, so those cancel. And that's all that cancels. So I'm left with minus 2yh minus h squared over h. And so I can factor an h out of the numerator, and I'm left with minus 2y, h becomes just minus 2y, and minus h squared becomes just minus h. 0 of that thing. So what is the limit as h goes to 0? We just found and simplified that difference quotient, and we got minus 2y minus h. So letting h go to 0, we get minus 2y. Right, so again, because we're taking the limit as h goes to 0 of a difference quotient, this is some kind of derivative. And here, since the y is the thing that was changing, this in fact is a derivative with respect to y. And we'll call this, when we get to 7.2, a partial derivative. So this is the partial derivative with respect to y. And see if you can figure out how to go from something like this to something like this, right? With just a general rule, maybe that's familiar to you. Okay, let's move on. And by move on, I of course mean that was the end of 7.1, and there's the homework for that. And there's Tucker hiding in a drawer. If you want, and I would encourage it a little bit, go ahead and pause the video here and just try a couple of the homework problems. Especially if you had any questions over what we just did, just try it a little bit before you continue and watch the 7.2 video, which is next. Okay, now we are on to 7.2, and 7.2 is going to be over partial derivatives. Right? That's all we'll be talking about is partial derivatives. I sort of introduced that in 7.1, and we'll get our grand introduction here. So just like when we first started talking about derivatives, when we first start talking about partial derivatives, we need to have some notation. So the partial derivative with respect to x, right, whatever that thing is, we'll find out some rules for that. Remember, we already talked about that's that limit as h goes to 0 of the difference quotient, where only the x is the thing changing. Right, so we call that the partial derivative with respect to x. We'll figure out how to take that in a second, and we'll have some rules for it. But whenever I'm looking for that thing, here is my notation. Right, if I'm starting out with a function of two variables, f of xy, then this delta f, del f, del x, that's this thing. That denotes the partial derivative. We probably won't use that. I prefer this thing in the middle much more, just f sub x. Right, so that says you take f, and then I want the partial derivative with respect to x. Right, so that notation is probably easiest. And if you want to leave the x and y on there, you can, but it's easiest to just use this one. The partial derivative with respect to y, very similar notation, but instead of an x, you use a y. And again, this guy in the middle is my favorite. It's easiest. That is a comma and not a y prime. So that is just f. Same thing with the x. Sorry if that's confusing. That's just fy, and this is just fx. All right, so this represents the partial derivatives with respect to x and y. So now, like I've said, we'll formally say it here, that partial derivative with respect to x, that was our notation from the last slide, is defined to be the limit as h goes to 0 of the difference quotient where only the x guy is changing and this y guy stays the same. So it's basically we're saying we want the derivative but only look along that x direction. All right, we want y to stay the same. I don't care about what y is doing. I just want to know how the x is changing. All right, and that is the partial derivative with respect to x. So how do we find that? You take the partial derivative by taking the derivative with respect to y, with respect to x, where you treat the y as a constant. So for example, if we have this function, to find fx, the partial derivative with respect to x, what we're going to do is take the derivative like normal, but whenever we see a y, a variable that's not the thing we're taking the derivative with respect to, we're going to treat it as a constant. And so what happens with that? So that means that fx, the partial derivative with respect to x, equals, so we're going to take the derivative of x squared just like normal, and we get an x squared. There was no y in there, so nothing silly happened. It was just 2x. Now we want to take the derivative of 3y times x, where we're going to treat that y as a constant. So really we're going to just think of this whole thing, 3y, as some constant. So how do you take the derivative of a constant times x? Well, the x goes away, and you're just left with the constant coming along for the ride. So the derivative of 3yx, the partial derivative with respect to x, is just 3y. You treat that y as a constant, so when you take that partial... Okay, so that was partial derivative with respect to x, and we'll see more examples of that. But let's look at the partial derivative with respect to y, right? So this is our notation for that. Again, this is the one I like the best. And that's the limit as h goes to 0 of that difference quotient where the y was the thing changing and the x's stayed the same, right? So in this, when we take this partial derivative, we're only looking along the y direction, and we don't care what x is doing. I just want to know, how is the function changing when that y is the thing that's changing and the x isn't changing at all? So we're going to find that by taking the derivative with respect to y. So we're going to treat y as our variable, and whenever we see an x, we'll treat it as a constant. So let's take the partial derivative of this same function, but this time with respect to y. Right? So partial derivative with respect to y. So if we're treating x as a constant, then x squared is still a constant, and what is the derivative of a constant? Well, it's 0. Right? So when we're taking the derivative with respect to y, there's no y in there with x squared, and so that's just some constant. We're going to treat x as a constant, so we take the derivative like it's a constant, and we get 0. Now we're going to add, well, 3 times y times x. We're going to treat x as a constant, so that's the constant 3 times x times the variable y. Take the derivative with respect to y, and the constant just comes along for the ride. In this case, the y goes away when you take that derivative, and the constant 3x is all that's left. And 0 plus 3x is 3x. So the partial derivative of this function with respect to y is 3x. All right, so now I'm going to throw a big thing at you here. I'm going to give you a function of two variables. Say find the partial with respect to x and the partial with respect to y. And then just plug in a point to each of those guys. So let's start by finding the partial derivative with respect to x. So remember, the way we're going to do that is to treat x as a variable, take the derivative with respect to it. And whenever we see a y, we're going to treat it as a constant. So let's start with x squared. We're taking the derivative with respect to x, treating y as a constant. So x squared, the derivative is just 2x. And that should be fairly normal. Now plus x times y, we're going to treat y as a constant. So how do you take the derivative of a constant times x? Well, you bring the constant along for the ride, and the x drops off. So since the y is the constant, that's what comes down. So that was the derivative of this piece. Now, what's the derivative of y squared, partial derivative with respect to x? Well, since we're taking the partial derivative with respect to x, we treat y as a constant. So y squared is just some other constant. So the derivative of a constant is 0. And now minus 2 genuinely looks like a constant, and the derivative of that constant would also be 0. So the partial derivative with respect to x would be 2x plus y. All right, so we found that guy. While we're here, let's go ahead and find fx of 1, 2. So that means we plug in x equals 1 and y equals 2 to that partial derivative. So 2 times x is 2 times 1, right? We're plugging into here. Plus y equals 2 is plugging in 2. And then that is 2 plus 2, which is 4. So fx, the partial derivative with respect to x, plug in the point 1, 2. So the partial derivative with respect to x at 1, 2 is 4. All right, now let's find the partial derivative with respect to y. So now we're going to treat y as our variable, take the derivative with respect to it. That's going to be the variable. And then whenever we see an x, we'll treat it as a constant. So let's start with x squared. X squared, if x is a constant, is still just some constant. And what is the derivative of a constant? It's 0. Okay, now plus, we're looking at x times y, where here x is a constant and y is our variable. So how do you take the derivative of the constant x times the variable y? Well, the constant comes along for the ride, the variable drops off, so we just have plus x. Now we're looking at y squared, derivative with respect to y. Well, that's going to be 2y. There's no x's around there, so just the regular old derivative where y is the variable, so that's 2 times y. And then minus 2, you take the derivative, that's a constant, derivative is 0. So our partial derivative with respect to y is x plus 2y. And now let's plug in the point 0, 4. So that means we plug in x equals 0, so that's 0 plus, and we plug in 2 times y equals 4, so that's 2 times 4, which is 8. All right, so again, to find the partial derivative with respect to x, we treated x as our variable and y as a constant. And to find the partial derivative with respect to y, we treated y as our variable and x as a constant. Notice that just because we have two variables next to each other, this is not like implicit derivatives where you have to do a product rule, right? Because we're treating one of those as a constant, it's just a constant times the variable, and you do not have to do a product rule for these partial derivatives if it's just x times y. All right, for implicit, you might have to, but this is not implicit, and so that is a key distinction, that for these partial derivatives, you do not have to do a product rule because you're treating one of those variables not as a variable, but as a constant when you take that partial derivative. That's this function, and try to find its partial derivatives. Right, so let's first try to find the partial derivative with respect to x. We do that. Notice that we've got an x squared guy over here, and then a natural log of x minus 3y. So those are two different functions that have an x in them and are being multiplied. So we'll have to use the product rule because there are two different x's being multiplied, two different functions of x, being multiplied. All right, so the first guy would be x squared. The second guy would be natural log of x minus 3y. Okay, so first guy, is x squared. So first times, now we need the derivative of the second guy. Again, we're taking the partial derivative with respect to x. So natural log, you do 1 over and copy it down. And then for chain rule, we want to multiply by the partial derivative of x minus 3y. So x has derivative 1, and minus 3y, well, that's minus 3y. We treat y as a constant because we're taking the partial derivative with respect to x. So we get minus 0. 3y is still a constant if y is a constant. But that's just multiplying by 1. So you don't need to write that. but you would have to if if it wasn't just a 1, right? So that was a times 1 for that chain rule, right? So that's the first times the derivative of the second. And then we're going to add the second. So copy down natural log of x minus 3y times what's the derivative of x squared? 2x. So that's the partial derivative with respect to x. Now let's take the partial derivative with respect to y. Well, here, this x squared is just a constant because we're taking the partial derivative with respect to y. So we treat x as a constant. So x squared is still a constant. But that's just a constant times natural log. So that's only one function of y, and that's this guy, the natural log, times some constant x squared. So we don't have to do a product rule here, right? So again, there's only one y in this whole thing. So we don't have to do a product rule. The x squared does not have a y in it, so we don't treat it as a separate function. It's just some constant. Okay, so how do we take the derivative of something like that? Well, the constant comes along for the ride. And now we need the derivative of natural log, so that's 1 over copy down what you see. And then chain rule, we're going to multiply by the partial derivative of x minus 3y. So the partial derivative of x with respect to y, we treat x as a constant and we get 0. The partial derivative of minus 3y with respect to y is minus 3. And so there's your partial derivative with respect to y. We could rewrite this, so that's x squared times 1 times minus 3. That's the numerator, so you could write that as minus 3x squared over x minus 3y. And that's the same thing, however you want to. Alright, now then, as it's baseball season, I'm going to throw you guys a curveball here. And it's going to be a function of 3 variables. You see what I did there, everyone? I hope you did. I hope you appreciate it. Anyway, it's a function of 3 variables, and I want to find a bunch of stuff. First, I want to find the partial derivative with respect to x. So how do I find the partial derivative of a function with 3 variables? Well, we're going to do the same thing we did with the function of 2 variables. Right? If it was just an x and a y, and I wanted the partial derivative with respect to x, I would treat y as a constant. But now since it's an x, a y, and a lambda, and I want the partial derivative with respect to x, I'll just treat y and lambda as constants and let x be the only variable. So what does that look like when you do it? Right? So let's find the partial derivative with respect to x. So we're going to treat y and lambda as constants. Right? So whenever we see a y, it'll be a constant. Whenever we see a lambda, it'll be a constant. Whenever we see an x, it'll be a variable because that's what we're taking the partial derivative with respect to. Okay, so the partial derivative with respect to x of this function, we start with an x squared, right? That's an x, it's our variable, so the derivative of x squared is 2x. Then we have minus y squared. Well, what's the derivative of y squared? It's partial derivative with respect to y. So we're going to treat y squared, the whole thing, as a constant since y is a constant. So that gives us minus the derivative of a constant is 0. And now we have minus lambda. Whoops. Lambda times a bunch of stuff. And so we're treating lambda as a constant. So what do you do when you take the derivative and there's a constant out front? Well, it just comes along for the ride. So we're going to leave the lambda out front and just take the partial derivative of all the stuff inside these parentheses. Okay, so the partial derivative of 4x with respect to x is just a 4. Then we have a minus 7 times y, but we're taking the partial derivative with respect to x, so we treat y as a constant. So 7y is still a constant, so the partial derivative of a constant would be 0. And then minus 10, that's obviously a constant. We take the derivative and we get 0. So what are we left with here? That's our whole partial derivative. We have a 2x floating around. And we've got a minus lambda times 4 here, so that's minus, I'll just write 4 lambda. All right, so we found the partial derivative with respect to x. Let's go ahead and plug in that 0.2 2, negative 1, 1. So I'm going to plug in x equals 2, y equals negative 1, and lambda equals 1. When I do that, I get 2 times x equals 2 minus 4 times lambda equals 1. So that's 4 minus 4 is 0. So there it is. There's that guy. Okay, I've run out of room, so I'm going to delete all this. So if you're copying it down, you should pause the video. All right, there we go. We already found fx, so we're good. We already plugged in that point, so we're good. Now we need fy, the partial derivative with respect to y. All right, so since we're taking the partial derivative with respect to y, we're going to treat all the other variables as constants. So whenever we see an x, we'll treat it as a constant. Whenever we see a lambda, we'll treat it as a constant. Whenever we see a y, that's going to be our variable. All right, so we start with x squared. We're going to treat x as a constant because we're taking the partial derivative with respect to y. So x squared is still a constant. So the derivative of a constant is 0. All right, now we subtract. We've got a y squared. We're taking the partial derivative with respect to y. So that's our variable. So we take the derivative like normal here with respect to y, and that gives us a 2y. All right, now we have minus. Again, lambda is a constant, so we've got a lambda times a bunch of stuff. And what do you do with a constant when you are taking the derivative and it's out in the front? Well, it'll just come along for the ride. So let's let lambda come along for the ride. And now we need the partial derivative of all the stuff in this parentheses. So what's the partial derivative of 4x with respect to y? Well, we treat x as a constant, so 4x is a constant, and the derivative of a constant is 0. Then we're going to subtract 7y, partial derivative with respect to y, that's our variable, so that gives us just a minus 7. And then we have a minus 10, derivative of that is 0. So what are we left with? We've got minus 2y, and then minus lambda times negative 7 is plus 7 lambda. Okay, so there's the partial derivative with respect to y. Now let's go ahead and plug this point into negative 1, 1. And that'll take care of this guy. We already found this. Yay. We need this guy. So plug in x equals 2, y equals negative 1, lambda equals 1. What do you get? Minus 2 times y equals negative 1 plus 7 times lambda equals 1. So that's positive 2 plus 7 is 9. So there we go. That's this guy. All right, again, I'm going to give myself some more room by deleting this whole slide. So if you're watching this and have not finished writing it down, I hope you've at least written it down by the time I finish talking. And if not, you should pause the video. Okay, gone. All right, we found fx, we found fy, we plugged in that point, plugged in that point. Now we need to find f lambda, and this will be the last thing, last partial derivative we'll take here. So we're going to now treat lambda as our variable, and all the stuff that's not a lambda, that's the x and the y, as constants. So whenever we see an x and whenever we see a y, we'll treat them as a constant. Whenever we see a lambda, we'll treat it as a variable. All right, so if x is a constant, x squared is a constant, and the derivative of a constant is 0, so that first term goes away. Now we need the partial derivative of a y squared, but we're also treating y as a constant, so y squared is still a constant, and the derivative of a constant is again 0. So that came from this guy. And now we've got minus lambda times all this stuff, and all that stuff is just x's and y's and a 10. There's no lambdas in there, so this is one big constant over here. All right, we're going to treat x and y as a constant, so 4x is still a constant, 7y is still a constant. Subtract them, 4x minus 7y is still a constant. Then subtract 10, still a constant. So that's just to say it's one big constant times lambda. And how do you take the derivative of a constant times your variable? Well, the variable drops off, and you're left with just the constant. And in this case, that looks like this. The lambda goes away, that was our variable, and we're left with the big constant. And so what is that equal to? Well, that's minus 4x plus 7y plus 10. So that is our partial derivative with respect to lambda. All right, now let's plug in that point. Negative, oh, not negative 2, sorry. Positive 2. Negative 1, 1. So x equals 2, y equals negative 1, lambda equals 1. So negative 4 times. Now we'll move on to second order partial derivatives, right? So you guys remember when we first started taking derivatives, we talked about higher order derivatives. So we would take the second derivative, talk about concavity or whatever, but we could also take the third, fourth, whatever derivative. We can do the same thing here with partial derivatives. So you can find higher order partial derivatives. We'll only really look at what we'll call the second order partial derivatives. It's the equivalent of like the second derivative of a regular function, function of one variable, that is. So if we're talking about second order partial derivatives, there's 4 ways to do that. So you could take the partial derivative with respect to x, and then do that again. That would be a second order partial derivative, which we would denote fxx. That would be second order partial derivative, first with x, then with x again. You could do the same thing with the y's. That would be a second order partial derivatives, where you first take the partial derivative with respect to y, then take the partial derivative with respect to y again. You could find fxy, so that would be find the partial derivative with respect to x, then look at that thing and take the partial derivative this time with respect to y. And you could do the opposite, where you take the partial derivative with respect to y, and then look at that thing and take the partial derivative this time with respect to x. And so those are called the 4 second order partial derivatives. So now let's find the 4 second order partial derivatives of this function. So we're looking for fxx, fyy, fxy, and fyx. Right, remember, those are our 4 second order partial derivatives. To find those first, we need to find the first order partial derivatives. Just like when we were trying to find the second derivative of a function of one variable, we had to first find the first derivative. To find the second order partial derivatives, we first need to find the first order partial derivatives. So we need to find the partial derivative with respect to x, and then we'll find the partial derivative with respect to y. So for the partial derivative with respect to x of this guy, here we have a composition of functions. We're going to need to use the chain rule. Right? So for e to the whatever, how do you find the derivative? Well, you copy down what you're looking at and multiply by the derivative of the exponent. And so in this case, we copy down the e to the stuff, and then we're multiplied by the partial derivative of 3x minus 7y. So the 3x partial derivative with respect to x, out pops a 3. And the minus 7y would be minus 0. 7y we would treat as a constant. And so that's just 3e to the 3x. That doesn't look like a 3 at all. Let's try that again. 3x minus 7y. Alright, now let's find the partial derivative with respect to y. It's going to be very similar. Right, you copy down what you're looking at. Minus 7y. And now we need the partial derivative of 3x minus 7y with respect to y. So we treat 3x as a constant, and it has derivative 0. And then we get minus 7 that pops out from the derivative of y. And so that's minus 7 e to the 3x minus 7y. Alright, now let's find all these partial derivatives. Second order ones this time. So for fxx, we go up to this partial derivative with respect to x, and we take the partial derivative with respect to x again. So we're taking the partial derivative of 3e to the 3x minus 7y with respect to x. All right, so that 3 out in the front, let's switch to green here. This 3 out in the front comes along for the ride. And then how do we take the partial derivative of e to the stuff? Well, just like before. Oops. You copy down the e to the stuff. And now we're taking the derivative again with respect to x. So we'll multiply by, just like before, only a 3 pops out. We treat x as our variable and y as a constant. And that's 9 e to the 3x minus 7y. So there is one of the second order partial derivatives. A very common mistake here is to just think as soon as you have 4 derivatives written down, you're done. But what we need is 4 second order ones. Right? The first order ones don't count, so we only have one of those so far. Right? So don't make that mistake. We need all 4 of the second order partial derivatives. All right, so let's find fyy. So that means we're going to go to the partial derivative with respect to y and take the partial derivative with respect to y again. Okay, so minus 7, that's going to come along for the ride, minus 7. And then we're taking the partial derivative of e to the 3x minus 7y. So for the e, chain rule, copy it down just like we have been. Of this function here. So find the 4 second order partial derivatives. So step 1, just like before, is going to be to find the first order partial derivatives. All right, so x to the 4 times y cubed, partial with respect to x. So we treat y cubed as a constant, so that hangs out. Then we take the derivative of x to the 4, so that's 4x cubed. And there's that first term. And now we need to subtract. We're taking the partial derivative of x squared times y to the 5th with respect to x. So the y to the 5th is a constant. It's just going to hang out. Times 2x. That's the derivative of x squared. All right, so that's our partial with respect to x. Let's find our partial with respect to y. This time we treat x's as constants. So x to the 4 just hangs out. The derivative of y cubed becomes y, or 3y squared, sorry. Again, x squared is a constant because we're taking the partial with respect to y, so that hangs out. And then y to the 5th becomes 5y to the 4th. So those are our first order partial derivatives, and we now need to find the second order partial derivatives, all 4 of them. So f(x)(x), right? This x says go look at this partial derivative. This x says take that the partial derivative of that guy with respect to x again. So we're looking at y cubed times 4 times x cubed. We're going to treat that y as a constant because we're taking the partial with respect to x. So that 4 times y cubed hangs out in the front. And then we've got an x cubed. So how do we take the derivative of that? Well, that's 3x squared. When we subtract, we have y to the 5th times 2x. So the 2y to the 5th is a constant. It comes out. And the x, when you take the derivative, just goes away. So we're left with 2y to the 5th. We could rewrite this, of course, as 12y cubed x squared. You don't have to. I don't care. But if you want to, some people might think that's prettier or something. All right, that's the first second order partial derivative. The first of the 4, that is. All right, back to blue. Yeah, blue. FYY. So that means the first y says, go look at this guy. The second y says, take the partial derivative with respect to y. Okay, let's do it. X to the 4 times 3y squared. The 3 times x to the 4 is just a coefficient, a constant. It's hanging out. And the y squared becomes 2y when we take the derivative. And we have minus x squared times 5 times y to the 4. So the 5x squared is a constant. It's coming along for the ride. We're taking the partial with respect to y. So y to the 4 becomes 4y cubed. And again, if you want to rewrite this, you can. That would be 6x to the 4 y minus 20x squared y cubed. All right. Now let's go to what we call the mixed partials. I don't know if I said that before, but mixed meaning instead of xx and yy, it's x and y mixed somehow. So the x tells us go to fx. That's this guy. That yellow is almost hard to see up at the top there. Whatever. Okay, so then the y tells us take the partial derivative with respect to y. Okay, so we've got a 4x cubed times a y cubed. So since we're taking the partial derivative with respect to y, the 4x cubed is a constant. It hangs out, comes along for the ride. And then we're going to multiply by the derivative of y with respect to y, which would be 3y squared. So that's that first term. Then we're going to subtract. We've got a 2x that's going to hang out because here we'll treat the x as a constant. And the y to the 5th becomes 5y to the 4th. And again, if you wanted to rewrite this, that would be 12x cubed y squared minus 10xy to the 4th. All right, before I take this second partial derivative, do you guys want to guess what it is? Good guesses, everybody. Let's see. All right, so fyx, that means you go to the partial with respect to y up here and take the partial with respect to x of it. Okay, so with respect to x means we treat y as a constant. So the 3y squared hangs out in the front. We get x to the 4, take the derivative, you get 4. Like I just said, notice that we do have this pattern showing up of these mixed partials, as I call them, being equal to each other. It turns out that this isn't a coincidence, and it will always happen if f is sufficiently nice. And for us, it will always be nice. Those things should always be equal to each other. And this was proved by a German mathematician by the name of Karl Schwarz. He did that sometime in the 1800s. That those things will always be equal to each other as long as f is nice enough. All right, let's change it up a little bit here. So we've got a function of two variables, and I want to find all the points x comma y so that the first partial derivative with respect to x and the first partial derivative with respect to y are both equal to 0. How do we do that? Well, for this, we'll have to recall some tricks from pre-cal about solving systems of equations. But that's okay. We can remember those as we go. So if we're looking for all the points where these are both 0, then we better find fx and fy. So what's the partial with respect to x? Well, x squared becomes 2x. The minus 3y squared doesn't have an x in it. We'll treat y as a constant. It's going to go away. Minus 2x, we'll get minus 2. And plus 12y, no x in it. We treat y as a constant. That goes away when you take the derivative. Okay, now we also want the partial derivative with respect to y. So what is that? Well, this time we treat x as a constant, so x squared goes away. Minus 3y squared becomes minus 6y. Minus 2x is a constant when x is a constant, so that goes away, and we're left with plus 12. So those are our two partial derivatives. If we want them both equal to 0, let's set them equal to 0 and solve for x and y. So up in the top, 2x minus 2 equals 0, so that's 2x equals 2, and x equals 1. So the fx, the partial with respect to x, is only 0 when x is 1. And this guy, we can solve, and we'll add the negative 6y over to get rid of a negative, and that's 12 is 6y, divide by 6, and you get y is 2. So the partial with respect to y is only 0 whenever y is 2. So the only point where both are 0 is when x is 1 and y is 2. All right, let's try a different guy, different function. Still want to know, find the points x comma y so that fx is 0 and fy is 0. So again, to do that, we'll first need to find the partial with respect to x. So what do we get? 4x cubed with respect to x is 12x squared. Then plus 2y squared x, we treat the y squared as a constant. So 2y squared is the constant out front of the x, so when you take the derivative, that's all you're left with. And we've got a minus 1 that's going to go away when we take the partial derivative. All right, now we want the partial derivative with respect to y. We do that, and we get, well, the 4x cubed is going to go away. Then when we take the partial with respect to y of 2y squared x, the 2x hangs out, and we're going to multiply by 2y, which is that derivative of y squared, and the minus 1 is going to go away as well. Alright, so that's just 4x. Wow, that's a really long equal sign. That's okay. That's just 4xy. Alright, now I want both of these things to be equal to 0. So equals 0, equals 0. Well, this fx guy looks a little difficult, so how about we just ignore it for now? Sure, that sounds like a plan. Let's go to fy. If 4xy equals 0, remember that just means that we have to set the factors equal to 0 separately. All right, so that means if we look at this as something like, how about 4x times y equals 0, that means that both of those have to be, I'm sorry, if either one of those is 0, then the other guy will be 0. I'm sorry, the equation will be equal to 0. All right, so set 4x equal to 0, and you get, well, x is 0. Set y equal to 0, and hey, that one was easier. Y equals 0. So fy is only 0 if either x equals 0 or y equals 0. But now let's go up to fx. If fy is going to be 0, then let's first take the case where x equals 0. So what we'll do is plug x equals 0 in and figure out when x is 0, what y do we get? Well, when we plug x equals 0, the 12x squared goes away, and we're left with 2y squared equals 0. So divide by 2, take the square root, and you get y is also equal to 0. So the f sub y is only 0 if x equals 0. And then based on this condition from fx, plugging in x equals 0 to that equation, we solve for, well, y is also equal to 0. So what that means is that the partial derivative with respect to x is only equal to 0 if both of these are 0, right? Since fy says one of them has to be 0, fx then says, well, if one of them is 0, they both are 0. What that boils down to is that the point, there's only one of them, where both are 0 is the point 0, 0. All right, so just talking through that one more time here. We went to fy and we got either x is 0 or y is 0. And we said, okay, that has to be true because we have an and. Both things need to be 0. So I know if fy is 0, then x is 0 or y is 0. So I'm going to start with the case where x equals 0. So I go up to fx and I say, what happens if x is 0? And I want to solve for y in this equation, right? Force it to be 0, but only look at the case where x is already 0. And so I looked at when x is 0, well, that meant y was 0. And so then, of course, if I plugged in y equals 0, I could trace this the other direction and get x is also 0. Right, so fy is only equal to 0 if x is 0 or y is 0. But then fx is only equal to 0 whenever both are equal to 0. Okay, so now to a word problem. Tucker's cat collar company, right, so she's making cat collars here, has a revenue in dollars given by this function, where x is the number of green collars, and y is the number of gold collars that she sells, right? So green, gold, Baylor, get it? All right. It says, what is Tucker's revenue if she sells 10 green collars and 20 gold collars? Well, okay, that just means we want to plug in 10 for x and 20 for y. That's not so bad. What we're looking for is r of 10, comma, 20. Okay, so that's 20 times x equals 10 plus 15 times y equals 20 plus 10 squared plus 2 times 20 squared. All right, if you plug all that in, what do you get? So same setup here, but different question. So this says use partial derivatives to approximate the change in Tucker's revenue if she increases her sales of green collars by 1 from 10 to 11. Okay, so using derivatives to approximate change, that should immediately be a big red flag that tells you this is about marginal change, right? Marginal change. So remember when we did marginal change, we took the derivative and plugged in our original value. So we're going to do something very similar here. We're going to take a derivative and plug in our original value of 10, but we're going to use the partial derivative. We're only going to take the derivative where the thing that's increasing is changing. So what's increasing here? She's increasing her sales of green collars, and that was x. X is the number of green collars. So if we look at our x, the partial with respect to x, that will estimate this change in revenue when her green collars sales increase. Right? So we're going to take that partial with respect to x because that's the thing that's increasing, and then we'll plug in that original amount 10, and that will give us the approximate change in revenue where only the green collars are changing, not both. Okay, so let's find that partial derivative. What do we get? Well, we get 20x becomes just a 20. 15y, we're taking the partial with respect to x, so that's going to go away. There's no x in there. Then we're going to add x squared becomes 2x. And 2y squared, no x in there. When we take the partial derivative, it goes away as well. So there's our partial derivative with respect to x. We want to plug in x equals 10, and whatever y value goes along with x equals 10, I'm not going to bother finding it because we don't need it, right? So that's okay. I just need to plug in x equals 10. So that's 20 plus 200. So that's 220. So the revenue will increase by approximately 220 if she increases her sales of green collars by 1 from 10 to 11. All right, so here is the same setup, but this time it's just a little bit different. So this says, again, use partial derivatives to approximate the change. So we should be immediately thinking here, again, marginal change. But this time it says, in the revenue, if she decreases her sales of gold collars by 1 from 20 to 19. So we have not dealt with marginal change where something is decreasing, but it shows up in the homework for this section. So I wanted to make sure you guys saw that before you tried that homework. So here's the way that works. It works exactly like if you were increasing, where you just take the derivative that's appropriate and plug in the original amount. The original, so not the lower one necessarily, but where you were starting from. In this case, we started at 20, decreased to 19. So what we want to do is take the partial derivative that has to do with the gold collars and then plug in 20, the original. So which partial derivative has to do with gold collars? Well, y represented the number of gold collars, so we want ry. So what is that? Well, again, we're treating x as a constant, so 20x goes away. 15y becomes 15. X squared goes away, and 2y squared becomes 4y. So that's the partial derivative with respect to y. And what we want to do is plug in, I don't care what x is because it's not there. It's not involved, and yes, I did that on purpose. And now we'll plug in y equals 20. Right, so do that. You get 15 plus what's 4 times 20? Yes, that's right. It's 80. So this would be 95. All right, so her revenue is going to decrease. I'm sorry, it's going to increase by 95 if she decreases her sales of gold collars by 1 from 20 to 19. Now I know you might be thinking, okay, well, how can the revenue increase if she's decreasing gold collars? But that has to do with, we didn't talk about the number of green collars, and maybe she makes more green collars if she's making less gold ones, or something like that. The idea here is just that for partial derivatives to approximate, you're going to take the partial derivative that has to do with the thing that's changing, and then if you're increasing or decreasing, whichever one it is, you plug in the original amount. Point 2, I know these videos were long, but if you've made it to the end, congratulations. Here's a picture of Sully laying on his back as a reward.